the mass which is changing, or what's called as mass flow. So that is the important, what we call as the mass balance with respect to the system what we are considering. Next, what we are doing is the component balance or the concentration control, which for that we need the component balance. So that component balance is again dependent on the molar concentration and obviously the number of moles and the rate of reaction of the operation, because in a CSTR we have the chemical which is going to be reacted. It's going to react and it's going to be converted into another form. So obviously we need to identify the concentration control. So we have, when we need the concentration, we are identifying the molar concentration of the system or the chemical which we are taking as the source, and the inlet and the outlet molar concentrations are identified. So once we are able to, and more, and all of us, we should understand one thing very clear, that only if these data which is there, which is available, then it will be easier for us to apply this and identify the controller, or sorry, identify the system model. So we have to have an idea or the details of the data for all these components which we are considering. So these are things which we are considering it. We are considering in a system that these are the things which are required for that particular mass balance. So for that we should have the details of all these components which we are taken here. For example, in the case of component balance, it should be the rate of reaction, molar concentration, and number of moles should be known. And or if we are going to take the mass balance, then obviously the densities, volumetric flow rates, the volume of the reacting mixture, these things should be known. Only when it is known, then it will be possible for us to create the model. Then obviously the third one will be with respect to the energy balance, because we are having a change in the energy change takes place. So obviously we have to go for the energy balance. So obviously that is also dependent on internal energy, kinetic energy, and potential energy. So we have the three energies which we are going to take into consideration. So that is the third equation which we are considering. So obviously we are getting an equation which is going to be with respect to the energy balance. So this is the last thing. Just a moment. Okay. Hello. Sorry. Am I audible? Sorry. Is it audible for all? Okay. Okay. Sorry. I just had a small interruption in between. Yeah. Okay, madam. A small interruption. I just okay. Okay. No problem. Okay. I'll just continue. Okay. So this is the thing which the third equation which you are talking about, the energy balance. So based on the energy balance, we are getting this expression. So once we have these three expressions, then we can go in for the mass balance. That's what I've written here. The final equation for the mass balance with respect to change in the flow, and obviously the component balance or the concentration. Based on the concentration, we are getting the concentration balance and the energy balance. These are the final expressions which you are obtaining for the corresponding continuous stir tank reactor. And once we are obtaining this, then obviously we have to go for the linearization, because obviously we know the terms are going to be nonlinear nature. So when it is nonlinear nature, it is difficult for us to identify an appropriate controller for that particular system. So the easier way is to go for linearized system to obtain an effective solution for a system for the system which you are considering. So obviously linearization is nothing but some kind of an approximation. That's what the main thing which you have to understand. And and everything depends upon the point at which we are going to consider the area in which we are going to consider the linearization, because the linearization is going to be in the form of if I take it in the form of a graphical output. In a graphical output, if we have a nonlinear kind of a system, obviously in the nonlinear system itself there will be a linear part. So obviously when we take a linear part, for example, I'll just probably take up a pen here. So I'll just draw here, see whether you get it. So just draw one small line here, just a rough curve. If I probably have a non-linear curve, non-linear nature like this of a system, so obviously what we are going to do is we are going to region or the point at which we are going to obtain the linearization. So if I consider this to be a linearized part, then I obtain put my operating point at this region alone, and then I do the linearization. So this or for this point again I do the linearization. So we do the linearization at different steps, and we identify the output so that we are considering only the linearized part. So when we take the linearization of the system, then we are able to identify an appropriate controller for this. But it need not be always be a perfect system, because we are not taking the whole system into consideration. We are taking only the linearized part. So obviously we are not going to get an 100% effective system or a controller, but we can get closer to it. That is the main advantage. So once, even if we are having a poor system which we are taking into consideration as a model, we can improve it by using our controller design. That is the advantage of process control and computer controller process. So that is where the challenge lies in. So even if you are getting a very poor kind of a model, we can improve it. So linearization, by doing linearization, it is not going to affect the system, but we should ensure that the properties of the system are kept intact, and they are not deviating. If you are deviating, then obviously there is no point in linearization. So we have to ensure that there is a deviation minimization. So we have to go for this regulation. So we have to identify this, whether the system is a regulatory system. So we are able to do the regulation. And obviously there is another concept called as gain scheduling. So we have to take this also into consideration when we go for the linearization. So these two things we have to identify, and we have to keep it in mind when we go for the linearization. Just move to the next slide. So obviously the linearization of the above equations, we are just going to do the linearization by the normal Taylor series approximation, or we can go for any kind of approximation technique. So that because of this, in this expression, this nonlinear term is going to be linearized. So obviously we go for the Taylor series approximation to linearize this system, to remove this exponential component out of the expressions which is shown here. So when we do that around a point, that is where this is the point which you are considering for where we are going to linearize, then obviously we are going to get expressions, and when we solve it, probably we will get a linearized model which is in the form of the expression which is given here. So this is the expression which we are going to get, and obviously we are going to do some kind of a mathematical manipulation, and then we are going to bring it into a simpler form. We are going to bring it to a simpler form like this. So this is our final expression which we are going to obtain. So from the complex expression, we are going to bring it to a simplified expression just for us to do the analysis. That is the idea behind. So analysis can be done easily when it is going to be a linearized system. So obviously once that is done, then we can go for the controller. So obviously the controller is going to be, in the case of CSTR, we can do the concentration and temperature control. We can take any, so once we have the expressions, then we can consider any of the input, and we can do a analysis. So this is one of our student, my student who did the concentration and temperature control for a CSTR, and they have used a PID controller for this. So it is just a normal expression which they have taken, and this is the model which they have put in, which is nothing but the concentration model. That is the expression for the concentration, expression for the temperature, and they have obtained a closed loop control for this. It's only a unity feedback they have taken for just for understanding purpose and for simple identification purpose. They have done this, and obviously this way the outputs which are obtained for the concentration control for an open loop response, and obviously for a closed loop response when it is going to be a PA controller. So all these things were only done abruptly with all random values. So a trial and error based approach only was done, and obviously for we are able to get an output like this concentration control. This is for a PA controller, and obviously for a PID controller. These were the outputs which are obtained for the corresponding concentration control, which we have done for the CSTR. And obviously temperature is a slow process, so obviously we can see here the temperature control. This is the temperature control by which you are obtained through the P controller, and obviously PI controller and PID controller. So these are just only the analysis which has been done. So you can identify, you can understand here. So once the mathematical model is created, then it is easier for us to do the analysis. That is the thing which you have to understand here. So that for that only purpose, I have taken this as an example, and I have just showcased it to you to give you that glimpse. So once this kind of a glimpse is given to students, then obviously they will get into an understanding that okay, for this purpose only, this probably this topic is going to be covered, and this is going to be taken. So that will be easier for them to probably look forward for the subject. And because it's being more into online now, so these things can be used very much for the students for their benefits. And obviously then you can probably talk upon the next type of control, because we are talking individual now, two different types of controllers. One is going to be for concentration and temperature. Next we can take a combined kind of control. It's going to be a cascade control. So this can also be taken as an example for when you go before when you start the multi-loop regulatory control, and given aspect or the concept of what is this cascade control, how this is going to be important as far as a MIMO system is concerned, then how this will be helpful for them for obtaining the output. So these things can be showcased to the students. And obviously this is what one of our students has done, the same thing. They have identified, they have done a cascade controller, cascade control system they have created, and they have done the cascade control for CSTR. And obviously you could see a change in the output for temperature alone. They have done for temperature alone this cascade control for the same CSTR which you have taken into consideration. Now the most important part, we are going to now come into the picture, that is going to be the MIMO process. So obviously when we talk about multi-input multi-output process, obviously it is not going to be a single variable, it's going to be multiple variable. So if we can talk about any CSTR, then obviously we have 9 different variables, 3 different modeling equations, and obviously the controlled and manipulated variables are going to be 2. Either it is going to be temperature, or it is going to be the flow or concentration. So that the things we have to first identify. So this is basically the important thing for any MIMO process, to identify these variables and the equations and the controller variables and the manipulated variables. Once we are able to identify this, then it will be easier for us to formulate the equations. So obviously this is a simple configuration when we talk in terms of MIMO process. So we have 2 inputs and 2 outputs. So obviously we have 2 controllers. So this is a typical MIMO process. Whereas this is another MIMO process with, if you can see here, the the first input or the second input and second output what you are obtaining. It is so the controller is taking action based on the second output, and obviously here the controller is taking action based on the first output. So this is what we call it as a process interaction. So we have to consider when we go for a MIMO process, the interactions which are occurring in the process. When it is going to be single separate equation, separate system, or a single controller, then obviously the process interaction will not be of that much importance. Whereas when you go for a MIMO process, that is multi-input multi-output process, obviously this is going to be a big aspect. So obviously we have to take this into consideration. So when we go for a multi-variable process, obviously the control systems that have only one control variables, that is not going to be a big problem, because that is a single input single output system. So that is not going to be of much problem. Whereas when it is going to be a MIMO system, that is multi-input multi-output problem, then obviously the variables and the process interactions between the control and manipulated variables has to be thought about, and it should be taken into consideration for controlling purpose. So before controlling, we have to identify the process interactions which are occurring between the control and the manipulated variables. That is more important when we go for a multi-variable process. So multi-loop regulatory is also based on that. So it is not something different. So multi-variable, multi-loop regulatory is almost go in hand. So this is some interactions which are taking place, especially some examples which is given here, which is more of an industrial problem. So when we take in terms of a blending system, so obviously the interactions will be between these 2 inputs. Or in the case of a distillation column, there will be interactions taking place at multiple points. Or when you take a gas liquid separator also, these are all chemical processes which are typically used in any chemical industries. So obviously our process control also comes into picture here. So that's why I've taken these 3 as an example. Already this is available in the net itself. So it's already available in textbook also. That's what I have taken. So that is the base. So it will be easier for us to actually explain to the students also based on this. So that's why these three examples I've just taken for giving you an understanding about what is process interaction, how it is going to be important. So each manipulated variable can affect the, but that is how many ever control variables are there, it can affect all the control variables. So it cannot be only one manipulated variable affecting only one control variable. It cannot be always to be there. Even one can affect many, or many will result into one change. So that those things have to be identified. That is what we call as the process interaction. So obviously this is the simple way of explaining a MIMO process. So we have a process. Obviously, the disturbances are going to be many, but a single input providing a single output with multiple disturbances. This is one type of an SASO process. Or we have two inputs, okay, and then two outputs. Obviously, that is also another type of single in. We'll call it as a uh, more amount of, that is multi-input multi-output process. That is going to be, the first one is going to be single input single output. This is going to be a multi-input multi-output, but more specifically a 2x2 system, which is going to be having multiple input and multiple output process. Whereas the last one, if you can see here, it can be n numbers of multiple input multiple output process. So these two are going to be as a part of MIMO, and this is going to be a part of SASO. So SASO is not going to be a bigger challenge, whereas obviously in the real time it's going to be more of an MIMO process which we'll be seeing, and for that only the controllers, that is identification of the controllers for this kind of systems are going to be a little bit tricky. So when you go for the multi-loop control strategy, obviously we have to identify the variables. So the variables includes the input variables, output variables, controller variables, manipulator variables. All these variables we have to identify. Then then we have to identify the type of controllers which we are going to use. So obviously if we have two inputs and two outputs, obviously will be having two type of pairings the controller. One is U with Y1, U2 with Y2, or U1 with Y2, U2 with Y1. This is what I showed you earlier. The type of pairings which can be done, and for only it could be if it is going to be n cross n system, then obviously n factorial possible configurations will be there. So this is what we can see here. Probably I'm just this is what I'm talking about here. And here we can see it U1 Y1 pairing U1 Y1 U2 Y2, or pairing U1 Y2 U1 Y2 and U2 Y1. This is another pairing. These are two pairings which we are considering, which we can normally take in terms of any controller pairings. So obviously when we have a transfer function model, so obviously we are going to have two control variables and two manipulator variables. So obviously we need four transfer functions are required, because it's going to be two control variables, two manipulator variables in the case of the earlier system. So obviously we'll be having either y1 by u1. So this is with respect to y1 u1, or y1 by u2, or y2 by u1, y2 by u2. So these are the four possible configurations. So based on that, we will be relating the input and output based on this expression. We are going to get this equations. These are two equations we are going to obtain, or we are going to get. So obviously we can represent the gains, or the earlier the gains which you are obtaining here. This we can represent it by using a gain matrix. That's what is this called as a transfer function matrix. The transfer function matrix at the steady state condition, that is S equals to 0, is what we call it as the process gain matrix. So this is called as the process gain matrix which you are obtaining, or the gain array which we are going to obtain. So this is actually a main important aspect with regard to any multi-loop system. So when we talk about the process interaction which is going to take place here, so obviously you can see here U1, we are going to give a controller. So obviously U1, when it's going to give an output, the controller will be G11. Obviously when it is going to be U1 with respect to Y2, it is going to be G21. This is going to be the interaction which is taking place between U1 and Y2, and obviously this is U2 with respect to Y2, and U2 with respect to Y1. We are creating another interaction which is going to be this G12. So obviously this is going to be the process which you are going to take, and the controller which you are going to fit here is going to be of this nature. This is going to be the controller which you are going to fit. So this is going to be the set point which you are going to create. and this is the feedback, and based on that we are going to give that input as an input to the controller, which is going to control the system here. This is going to be the interaction which is going to take place. So for the interaction we are creating this kind of a setup. So this is what is in terms of closed loop which you are talking about. So either we are going to control the output y1, so through these two, that is the blue line which shows here, or we can control y2 with respect to the lines which is shown here, with three red lines. Okay, so it is either through the blue lines which you are going to control y1, or it's going to be control of y2. So these are the two things which is called as, this is totally called as the control loop configuration. This is the control loop configuration for this kind of a system which is having two inputs and two outputs. That is called as a multi input multi output system. So for that only what we are going to identify is, this is the one which is identified by a person called as Bristol, which is called as the relative gain array. So the relative gain array is going to be the array which is comprising of all the gains of the different loops. So once we are able to identify that, it gives a better understanding about the system, and it is going to be easier for us to go for the appropriate controller. That is the advantage when you go for a relative gain array method. So only the knowledge about the steady state gains is required here, and the dynamics is not required. So that is another advantage of going in for this relative gain array. You need not have a in-depth knowledge about the dynamics which is going to change, or the changes which is going to take place in the system. So when it is in steady state condition itself, what is the gain which you are going to obtain, that is more than sufficient for identifying the relative gain array and doing the analysis based on relative gain array. So what we are going to do here is, in the case of a relative gain array, obviously, as I told you, what we have obtained above is nothing but the equations, as I showed you here. These are the equations which we are going to obtain. How we are going to get those equations is shown here as a step-by-step method. So what we will do here, obviously, the loops have to be opened, the controllers have to be detached, and by keeping one input as constant, and we introduce a step input in another one, and this will result in a gain. So that gain we are going to identify the first one. Now the same thing will be done in loop 2 by doing the same thing, by keeping one as a constant and giving a step input to the other. That is, we are going to keep maintaining y2 as at the desired point, and introducing a step point in u1. That is going to result in another expression. So this will indicate direct as well as indirect effect. So one will indicate the direct effect, other one will give the direct as well as the indirect method, the effect on the system. And when you are able to find out the gains, that is, this gain divided by this gain will be nothing but what is called as a relative gain. So one is going to be a direct effect, other one is going to be a combined effect. So these two things which will be taken into picture, and for that we are finding out the gain which is called as the relative gain. So this relative gain for the first loop, that is for the first loop which we are going to take into picture, is going to be lambda 11, which we are taking here as an example. Next, when we talk about the similarly, we can take it for all the other loops also, which is going to be effectively going to be lambda 1 2, lambda 2 1, lambda 2 2. So it's going to be for all the 4 loops which we are going to take into picture. So for the all the 4 conditions, we can take we can find out the relative gain, which is going to be in terms of lambda 1, lambda 1 2, lambda 2 1, lambda 2 2. So obviously each and every relative gain has a property that is given as the properties of the relative gain array. So if you can see here, if lambda 1 1 is 0, then obviously u1 does not have an effect on the output, and they should not be paired. So this is the conditions which has been put forward as a property for RGA. So likewise, if lambda 1 1 is equals to 1, then obviously it does not have an effect on the output, and it is completely decoupled. So we can these are some of the properties which we can keep in consideration whenever we talk in terms of identifying the controller. So when we go for a controller, then we can obviously take this into picture. That's why the advantage of relative gain array is very much essential for us to identify whether the system is completely decoupled or it is weak coupled, because whenever you go for interaction, that is whenever process interaction occurs, obviously you have to understand that when we put a controller, a single controller cannot take care of the process interaction. So what we do here is we decouple the system and then we apply the controller. So that will be a better method when we go for effective control. So otherwise the stability and other aspects will be a bigger problem, as well as the gain also will be a bigger problem to maintain. So that's why we go for this decoupling. So for decoupling the system, we have to understand whether the system is possible for this decoupling, or whether it cannot be done. So that's why we have this relative gain array as a main aspect for identifying these components. So obviously, when you see here, when lambda 1 is less than 0, it has another effect, that is, it has a strong effect on in the opposite direction. So the interaction effect is dangerous and detrimental for system. So we should not take this value of lambda 1 less than 0. So obviously, it should be either equal to 0 and between 0 to 1. It should not be less than 0. And similarly, when you take a relative gain array of this manner, then obviously it's considered the system is completely decoupled, which is going to be an ideal condition. So this is an ideal condition for any system, so which we call it as an ideal system. And similarly, when we take it in the reverse direction, it is going to be a different condition, that is going to be a decoupled in reverse manner, which is called as an again ideal condition. And obviously, when it is of 0.5 value, then we have a consideration that it's having a strong interaction and does not matter for even pairing or when it's resorted to. And finally, the last one, when it is greater than 0, so when it is less than, that is between 0 and 1, this is the condition. When it is again greater than 0.5 and this one, then this is going to be the condition. So these are the conditions which we can identify or understand from the RGA, which is nothing but the properties of RGA. So this gives us a better picture about whether system can be decoupled or not, and how it can be done. So this is what we do for a decoupling. So we are going to identify the process interaction. So obviously this is going to be the process interaction which are going to take place. So obviously from equation 1, that is, if I go back above, you can see here, this is equation 1. So from this equation 1, we are obtaining the expression here for u1 dash. Similarly for u2 dash, we are obtaining the expression. Now we are putting this as an expression where u1 dash is nothing but equal to this expression, u2 dash is equal to this expression. So when we are able to get this, then what we are doing here, we are finding out y1 and y2 from this 3 and 4. From this 3 and 4, we are finding out this y1 and y2, and based on that, now what we have done here, we have done a decoupling. So from this coupled system, or what we call as in process interaction, we have done a decoupled, or we have identified a decoupled system. We have splitted, or we have decoupled the system into two different systems. Now it will be easier for us to apply the controllers and we to obtain the output. So that is the advantage of going for a decoupled system. So the same thing what we have done here, I have done here is I have taken the example. My students have taken this CSTR as an example, and they have gone for this decoupling technique. So transfer functions were obtained for concentration as well as for temperature. So these were the linearized equations which were obtained, and for that decoupled design system was done. So we can see here, this is a response of a decoupling method for concentration control. So for concentration, we are able to obtain a decoupled by using the decoupled design method. We are able to obtain the control design for concentration control. And we have not done for temperature, but we have done for concentration control. And these were the various the parameters which are obtained. That is the controller parameters and the error parameters which are obtained for the controllers which we have used. So we have tried in for, actually earlier we could see here, we could try for P, PI, PID, and probably the decoupler will give a better response. And probably last one is going to be fuzzy logic. Fuzzy logic will be giving a much better response, but again, it depends upon the type of the controller which you are designing. So obviously that will not touch upon at this moment. We'll stick upon with this decoupled system itself, or decoupled control itself. Okay. And obviously I have another probably 10 minutes more. I'll just touch upon the last important point, which is going to be the biggest log tuning method. So what we are seeing here is till now is the importance of the relative gain array and the interactions which are taking place, and how to probably understand these interactions in terms of the relative gain array, and how we are going to probably do the decoupling. So I've taken a single example and probably shown to you, but it involves a lot of techniques, a lot of equations. So it is obviously better if it is given in elaborately and explained. So what I've given is only in nutshell what has been done here. So obviously the last one is going to be the biggest log tuning method. So this is the most preferred method when you go for a multi-loop PID control. So when the PID control is going to be of multiple loop, then when you go for a multi-loop PID system, then we go for this kind of a detuning method. It's called as a detuning method. So what is this detuning is? We are going to identify the controllers and we are going to design the each controller based on the process interaction, and we are going to ignore the process interactions. That is, we are going to do the decoupling and then we are going to do the control technique. So that is what is called as detuning. So once we are identifying the process interaction and ignoring it, then the interactions that are taken into account will be applied for this controller, and we are going to do the detuning. So it's nothing but the similar to that of our PID tuning only, the Ziegler-Nicholas tuning only, that we probably do it, and we apply this as a technique. And here there is one tuning technique which is done by this person. It's called as the Tyrus Liban method, tuning method, where he has given a specification for this detuned system. So this is our normal Ziegler-Nicholas setting. So from that, these Tyrus Liban has derived these settings for for the PI and PID controller. So that what we do here is we going to use it for what is identifying the log modulus. So when you take a log modulus for a single loop, then obviously we have the controller as well as the system. So that we are going to take in as a log modulus based on that. So for the control system, we are going to find out the log modulus and we are going to take the LC max value of this, and we are going to identify the system based on that. This is for a single loop. If it is going to be a multiple loop, then obviously we are going to define the expression based on the matrix which you are going to identify here, and based on that we are going to see to that the maximum the LC value does not cross this 2n, where n is nothing but the dimension. So if it's a 2 cross 2 means, then obviously does not cross the matrix does not cross 4 by 4. So that's how we are going to identify the the the, the the controllers for both single loop as well as for multiple loop. Single loop is not going to be a problem because that is going to result only in one equation, whereas multiple loop is going to result in many equations. But we have to understand that the dimension of a should be only equal to 2n. That's what the law actually states. So how this is done here is based on the Ziegler-Nicholas PID settings. We are going to identify the ultimate gain and ultimate time period. So obviously there a factor is being assumed. So based on that factor, new controller parameters will be set, and then we are going to compute the matrix, W matrix, and for that we are going to identify the LC max, and we are going to ensure that the LC max does not equal to 2n. If it is equal to 2n, then obviously then we have to stop. Otherwise, if it is not equal to 2n, then we have to select new values and return until it's going to be equal to 2n. So if it is not equal to 2n, you ensure that it reaches 2n. Otherwise, when it's 2n, then obviously we are able to obtain the required controller for that particular system. So this is what is the biggest log tuning method, which is done especially for controlling the multi-loop systems and for multiple loop control. So obviously this is the main things which is probably required in my aspect for unit 4 because unit 4 is more into the application. I would say the application will be more with regard to multi-variable control that we'll probably cover in the next unit. But to understand the multi-variable control, you have to know the multiple loop regulatory. So the regulatory system you have to understand. In that we have the relative gain array, which is going to be very important as far as the concern, and then how the process interactions are going to affect, and how we are going to go for the decoupling, and finally the the controller design based on the biggest log tuning method. That is what is the last part of this topic. So that's all with regard to my presentation. If there is any queries, I'll take it for another few minutes, then we'll probably wind up. I'll probably stop sharing.
Okay, sir.
I think I've stopped sharing. Yeah. Why it's not showing? Okay. Yes, madam. Actually, I'm through, madam. So
Yes, sir.
thank you one and all for your patient hearing. Uh, if you can permit me, probably I have a meeting at 10:30. So uh, if I could probably leave, then it will be fine. Or is there any questions if if you want to ask, you can ask. So we can wind up.
Staffs, do you have any doubts? Okay, sir. Thank you, sir. Thank you
Okay,
for
madam.
accepting my invitation. You have shared your information regarding multi-loop regulatory control, introductions of process interactions, and you have given what all the important points should be shared to the students. Under busy schedule, thank you, sir, for accepting our invitation.
Thank you, madam. Thank you all for your patient hearing, and thank you for giving me this wonderful opportunity. Thank you. Thank you. I
Yeah,
leave. I
thank you.
can I leave, madam?
Yes, sir, you can leave, sir. Thank you, sir.
Okay. Thank you. Thank you. Thank you.
Yeah, thank you, sir. The next session will be starting at 11 o'clock. Thank you.